Hello, welcome to Lesson 8 of CE 3372, Water Systems Design. The topic of this lesson is demand estimation. We're going to take a brief look at the modeling protocol, and then we'll go into the details of demand estimation. So, we spent the last two lessons learning how to analyze a pipeline network under different conditions, and one of the begging questions is, what's the point? And the point is to allow us to answer questions like indicated in this picture, which is, what is the flow distribution if the demands are changed as shown? So if the demand at C down here is changed from the 0.5 CFS to 0.4 CFS, and demand is added here at node 3, how are the flow rates and the pressures going to change in the system? And that's a useful question to ask, especially if you as a designer or an operator are contemplating making such a change. Better to do it in the model and learn if it's a good idea or not than to do it for real and then have to scramble to satisfy demands and pressures and whatnot. So the network modeling protocol I suggest, and this is whether you're using a spreadsheet or the professional tool, EPANet, is to sketch the network on paper, label the nodes, give them meaningful names at least to you, label the links, give them meaningful names, label the supply, and label the demands. And the demands have to be estimated in advance of attempting to run a model. Next, if you're doing it by hand, you'll want to build the node arc incidence equation. So those are the continuities at each node. After you've built those, so that's the matrix that has ones and zeros in it, and then the right-hand side is equal to the specific nodal demand. Then build the pipe head loss equations, and that's the head at the starting node minus the head loss equals head at the end node, and rearrange that so you get that diagonal of the script L coefficients, and then the lower right corner, which contains the beginning and end node indicators for the nodes that you're trying to find the head for. Then build and run the computational tool. In the case of a spreadsheet, you'd make an initial guess of flow rates and node elevations, execute in node heads, execute the computation tool, update the guesses, and continue until you have a flow balance and a zero error term, or stop and debug your spreadsheet tool if things seem to be going awry. And that becomes obvious quickly. The heads go the wrong direction. The f of x term does not go to 0. So here's what's meant by a sketch. The nodes are labeled here with squares, the pipes are labeled with P's, the flow directions are indicated, and then the demands at nodes 3, 6, and 7 are indicated in this drawing, and then a supply of 3 cubic feet per second is shown here going into node 1. If we were unaware of the connection from the supply reservoir into the network, we could conceivably replace node 1 as a fixed grade node, as we did in one of the earlier examples if we're doing our spreadsheet solution. Alternatively, we can just connect it to a reservoir of arbitrary head and then determine the correct head later, or an appropriate head later. Once the tool is built, then we can ask the what if questions. So we can change flow distributions, we can compute flow distributions as demand are changed. And here is a spreadsheet that does those calculations for the pictured conditions. And the spreadsheet looks elaborate, but really it's just an extension of the rows and columns using the same methodology that we did in the in-class examples. It requires the analyst to insert rows and columns with some forethought, but after that's done, you now have a tool that will let you analyze that particular network until you're blue in the face. Next, we're moving into the network design principles for a water supply system. Um, and water supply includes all aspects of the supply, so it includes the actual raw water, treatment, other facilities, pumping facilities, transmission lines, and ultimately the local distribution network. And all those bullet items can be represented in a hydraulic model if necessary. The distribution network consists of items that are designed to convey potable water, and the key things that we're interested in as design engineers or operation engineers is at adequate pressures and discharges. The system is comprised of components such as pipes, fittings, valves, and other appurtenances. So that's a fitting that doesn't fall in any other category. Who does the design? In some cases, the people at the water company themselves do it. The actual work is going to be carried out by engineers or consultants that are engineers. The engineering aspect is required because, at least in the Texas code, it's specifically stated that a professional engineer has to sign certain aspects of a water system design. What about the design parameters and regulations? Well, we get those from the State Board of Health, local city and county health departments, EPA, American Water Works Association, American National Standards Institute, and our state regulations. So there's no real secrets other than to fit things into right-of-ways that aren't necessarily available. The design requirements that we're especially concerned with in municipal distribution systems are the water pressure in different parts of the system, the water velocity, the age of the water, if chlorine or chloramine is the disinfectant, the chlorine concentration, replace the word chlorine with disinfectant concentration, and fire flow. And of those, fire flow is by far the most vague in any of these. The velocity is important because if the water is flowing too quickly in a pipe, it can damage the pipe. If the water has to be turned, the forces involved actually get substantial. So we're targeting locations to find where the velocity is perhaps unexpectedly high, and then we would engineer to accommodate that, either strengthen the physical structure to handle the forces involved or change the diameter to slow things down. Okay, so the pressures have to be high enough to overcome the head losses in the system, as well as provide positive pressure in case there's a breach so that contaminated water can't leak back into a distribution system, but not so high, not too high so that we don't damage fittings and other appurtenances. The main thing is valves. If the pressure is too high as we open and close valves, which we have to do, at least at the house level, over time the valve seats destroy themselves if the pressure is too high. And too high is in the 100 psi range. Now we can certainly buy valving that can handle high pressures, but it's substantially more expensive than the valving that you would normally put in a residence, and so instead we try to reduce the pressure at least when it gets close to the customer. Often municipalities use concept of pressure zones, and so these are areas with min and max within the system, and we adjust the pressure zones using storage, boost pump, or pressure control valves. A lot of this can be managed with pipe size, and a lot of it's forced upon us by topography. If we're in parts of the country where we have vertical elevation changes over our system, we might have water running up a hill that needs to be boosted or coming down a hill that's going to need to have its pressure controlled. We often generate these pressure zones to increase reliability of the entire system to meet fluctuating demands. I think we saw a sample of that when we discussed storage concepts. System pressures get adapted to requirements, so in hilly areas there's often booster pumping and pressure reducing valving. Minimum pressures vary from state to state, but they're not going to vary a lot, which isn't to say that you can just memorize one and get away with it. Just be aware that as you move to different locales, the minimum required pressures can vary. These are established by the health department or other agency of the state. And then there's also a fire component, since most water distribution systems are also used to provide water for firefighting capabilities. The fire marshal of the jurisdiction has input on additional pressure requirements that need to be adhered to. So for fire flow, there's several ways suggested in the various readings for the class. Each municipality can establish it based on local conditions. For example, in the Houston Infrastructure Design Manual, there's a specific statement of what the fire flow needs to be at a fire hydrant and the hydrant spacing. Alternative ways are some various formulas published by something called the Insurance Services Offices, and the tool that these appear in is something called the Guide for Determination of Required Fire Flow. It's a pretty thick book. It recommends these criteria for a couple of reasons. One, to establish insurance rates, and secondly, classifying a municipality with reference to fire defenses and physical conditions. An example of a formula that might come out of an ISO document is shown here in the slide, where Q in gallons per minute is equal to 18 times a constant times the square root of the floor area in square feet. And then the constants vary depending on what type of structure it is: wood frame, ordinary, fire resistant, and so forth. As I just said earlier, the City of Houston Infrastructure Design Manual has specific instructions for locating hydrants and required flow to these hydrants. Other municipalities have similar guidelines. Your design project that you do as teams, it's coming up pretty soon. The guidance you're going to be instructed to use is the Houston Infrastructure Design Manual. There's nothing special about the Houston Manual. I just happen to have a copy on the server, and it's representative of what you would do working in any municipality in Texas, except of course you use the correct manual. Water supply system has hydraulic characteristics and service characteristics. The hydraulic characteristics are things like pressures and discharges, and they're a function of the hydraulic conditions. The length of pipe, the size of pipe, and the pipe condition matters. If you look at the Hazen-Williams formula, you'll notice that the pipe condition in terms of age affects the Hazen-Williams C factor. The service characteristics include demand as it relates to present and future population, the economic base, fire flow, and climate. If we're to look carefully at the Texas code, we'll see that most of the flow needs to be computed for today and for 50 years into the future. So the implication is that the service life is at least 50 years, and you're expected to design for the anticipated population increase. I don't think we ever pretend there's a decrease, and if you do it all right, then your kitty cat will have plenty of water to drink from the hose. So the water utility is who is responsible for quality and operation of the distribution system. They can be companies, either public, they exist for the health, safety, and welfare of the public, or privately owned utility that provides water for profit. Both of these exist in the United States. They're both effective. They produce quality water, and the health and safety of the public is generally not threatened, Flint, Michigan being a recent notable exception. The profit motive is thought by some to decrease the incentive to maintain things and let the stuff break, and then it becomes nationalized, taken over the public, repaired, and then the private people come and operate it again. I frankly don't know. I can't think of any instances where that's really true with regards to water supply. There's probably elements of truth to that. The critique of the public entity is that they do things slowly, and that's a fair argument. It's the way public things are funded and the amount of transparency that's required. So I'm not trying to advocate for one or the other form. They both exist, not just in the U.S., throughout the world, and they both successfully provide water to customers, and they do it through a distribution system that is designed by, wait for it, engineers. So water supply systems can be gravity-fed, booster pumped, or pumped with storage. Gravity is desired because it's dependable. It requires that the source of supply is located quite a vertical distance above the city, and high pressure demand for firefighting may require pumping trucks. City of New York, a large component of its supply is gravity fed from, I think, the Catskill Mountains. City of San Francisco has a pretty decent gravity supply from Hetch Hetchy Reservoir near Yosemite Valley. Once it gets to either of those cities, there's pumping that has to be done to actually get it to the end user. But the raw water supply comes in pretty dependably. A booster pump system is probably the least desirable for a couple reasons. The pressures vary with variations in flow. That can be mitigated with machinery, but it provides no reserve if there's a power failure. So if it's a booster pump system and the power fails, the pumps shut down, the check valves close, and nothing's going on until electricity is restored. The city of Houston, as a greater metropolitan area, is largely booster pump supplied. I mean, it has some elevated storage, but without electricity, the ability to move water around Houston is pretty limited. Pumping with storage is probably the most common in smaller communities, a couple 100,000 or less. Lubbock is a good example with that, is that a lot of the pressure zones in Lubbock are actually based around elevated storage tanks. And the water is supplied at roughly a uniform rate using those flow equalization calculations that we discussed earlier. And then flow in excess of consumption is stored in elevated tanks, and it guarantees a fairly constant pressure, at least in the vicinity or the area of the tank that it can provide that pressure. The pipe system itself is usually categorized in primary mains or the arterial mains, and they form the basic structure of the system. These are fairly large diameter pipes that carry flow from a pumping station to elevated storage tanks and carry flow from elevated storage tanks to service areas. They tend to be laid out in interlocking loops. The mains themselves are usually not more than 1 kilometer apart. They're valved at intervals of roughly 1.5 kilometers, and then the smaller lines that connect to them are valved. The valves are everywhere to be able to isolate the system as well as provide some other flow controls. The secondary lines form smaller loops within the primary main system. They run from one primary line to another. They're spaced on the order of 2 to 4 city blocks, and they're capable of providing large amounts of water for firefighting without excessive pressure loss. So many of our fire hydrants are connected to these secondary lines. Then there's the smaller distribution lines, and they form the grid over the entire service area. They supply water to every user and fire hydrant. They're connected to primary, secondary, or other small mains at both ends. They're valved so that portions of the system can be shut down for repairs. The size may be dictated by fire flow, except in residential areas with very large lots. The size in Texas is, the minimum sizes are specifically stated in the RGE 195 that you did for homework assignment 2, I believe. It has minimum pipe sizes based on the number of anticipated connections. So at least in Texas, you could start out with a minimum logical pipe size and grow your design from there, and you would be you'd be certainly complying with the rules, but those are based on a lot of years of experience, and so you'd be relatively assured that you'd probably have a feasible system, possibly with some pumping changes or storage changes, or maybe a few lines that have to be adapted. The water supply system is comprised of these 7 major categories. The raw water source, it could be a lake, a river, an aquifer. The treatment facility, so the raw water comes into the treatment facility. Our environmental engineering colleagues go ahead and take the raw water, which is technically yucky, and they add flavor and sugar and some other things and make it into yummy water. We call that water potable because it can be put in pots not portable. It's still heavy. And the potable water is then um, moved either by gravity or by pump through transmission lines into the distribution system. The transmission lines, there's raw water lines. They would bring water from the source to the treatment facility. And then there's large diameter transmission lines to take it from the treatment facility and get it out to the smaller parts of the network. There could be intermediate storage facilities. Their purpose is to stabilize line pressures, provide reserve for peak demand, and possibly provide storage for fire flow and emergencies. And this photograph has the peach, so that must be Georgia water. Then the distribution lines themselves convey the water from the storage to the service areas. They're typically in either looped or grid or branch layouts or a combination of the two. And then the appurtenances are all the other little bits and pieces that make up the system. Valves, auxiliary pumps, fittings, fire hydrants, and so meters, and so forth. A water distribution system is a water use system. So its capacity is based on the population served. And that's important because that's going to segue into how we determine the demand or the capacity that the system needs to have. Water is used for a variety of things. There's two major categories of use, consumptive and non-consumptive. Consumptive use means that when the water is done being used, it's no longer fit for that use. It's been consumed. Doesn't necessarily mean disappeared. So municipal water comes into the pipe distribution system, goes through kidneys and colons, and after it's done that, it's not particularly yummy anymore. It goes from the yummy water to the yucky water designation. Agricultural water, um, there's still a substantial amount of waste just by it's not by the nature of how we do things, more by the necessity of providing enough water to fight salts and other dissolved compounds that could otherwise destroy crops. The runoff water from that is usually quite not usable as is. It contains leftover fertilizers, leftover um, insecticides, herbicides, and whatnot. And then mining water, same thing. After it's been used for mining purposes, either solution mining or hydraulic mining, or as part of the extraction process, the water itself is quite contaminated. So that's what's meant by consumptive use. Non-consumptive use are things like hydropower. So we run water through the turbines to make electricity, and other than the water being in a different location, it's still usable for either that purpose or other purposes. Water used for transportation is considered non-consumptive, assuming we don't spill a big old load of methyl ethyl death into it. And then water used for recreation is non-consumptive. So the water demand is the quantity that consumers use per unit of time. Examples are things like million gallons per day or liters per second, just to use a arbitrarily much different scale unit. And these depend on the population, the climate, the industry, and other economic factors. So residential demand, things like single-family, multifamily apartments, the water is used for drinking, landscape, swimming, fire, street cleaning, and there's usually two demand peaks, morning and evening. And in this particular diagram here, this is a special residential apartment that has an additional demand because to get to the ground floor, people put on their swimsuits, and they climb up into the dragon's mouth, and then they slide all the way down to the ground, come off, shake themselves off like a puppy dog, and they go on to work. That'd be cool if that was true. I just made that up. Commercial is uses for like motels, hotels, offices, shopping centers. Usually the peak demand is quite a bit less varied than residential. It has a peak demand, but the 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 height of the peak isn't quite as abrupt as it is in a residential. And then industrial demand, chemical plants, food processing, mines, water used for fabrication, cooling, petroleum refinery. The actual water use depends on the type of the industry, and usually industrial users are very cognizant of what their water needs are. And certain industries won't even trust us to provide the water. They'll go ahead and provide it for themselves. but they still need engineers to do it too. So whether we're designing for a residential commercial world, typical municipality, or for an industrial world, the principles are the same. To assign demand for our network models to allow us to do what-if calculations to be sure we're supplying water at proper flow and pressure, we need to have some way of estimating the demand at a link or at a node. So network models contain nodes, and they usually represent a multitude of actual connections. It's conceptually possible to model down to every single meter. Generally, it's not done because the model itself is hard to maintain, even today, even if a magic cyborg AI was doing it. Computers can make small errors too, and they would go unnoticed perhaps for a long time until something really unexpected happened. And frankly, the operation of a single connection is not well known, at least at the time of this writing. With the emerging smart meter and smart technology, that may not be so true a statement in a decade from now. Once there's been enough smart meter data collection, single connection behavior might indeed become very well known. And the benefit to designers is the input to their models can be more accurate. For the time being, we have to accept a less accurate point of view. The different types of network are branched. These, there's no circulation. They look like branches of a tree. It has terminal connections, which are dead ends. The water in the dead end is stagnant. If there's disinfection residual, it gets used up in that dead end, creates corrosion. There's no disinfection residual. The water goes from yummy to yucky, and if you drink it, it makes you dead. Hence, that's the name dead end. Unless there's literally a demand at this location, the water's not going to move here. So it only perhaps moves a couple times a day, if at all. And water sitting stagnant, using up disinfection residual, can corrode the interior of the network. A preferred from a water quality and actually hydraulic management is a grid or loop system. And so water comes to a particular junction from more than a single direction. So the water's, as long as there is non-zero demand somewhere in this network, the water's going to circulate. In some cases very slowly, but it moves. Hence the water age in the system is younger, it's technically fresher, so the disinfection residual has the ability to do its job, and presumably the oldest water is still young enough to have a disinfection residual. In the case of a water main break, fewer customers are inconvenienced. If a single water main breaks, it can be valved off, and because water comes from multiple directions, it's quite possible to maintain a higher level of service. And here's an example, loop versus branch. So every link in a branch system is a single point of failure that isolates all downstream nodes. That's not the same. It's not so with a grid system. So look at the picture on the right and the picture on the left. They both have the same node layout, so they're both serving the same amount of customers. Both would work if everything's worked, but if this particular main right here were to fail, everything downstream of that is denied water. So if these were important people, you'd lose them all. I guess that's one way of doing urban renewal. In this case, if that same main breaks in the loop system, only the customers immediately along the portion where the break would be denied water. The rest of the system could still provide water, albeit probably at a much lower capacity without that main until it's repaired. So there's a certain redundancy built in a looped network. So demand estimation is used to determine how much water an entire system is likely to use. Flow rate estimation from a plumber's perspective is used to determine how much capacity a system should be able to provide for a particular pipe size. And then demands are declared to occur at specific points in nodes that correspond to multiple customer connections. So these ideas give us a way to estimate demand. One tool is something called the USGS Circular 1200. It's cross-linked in the course notes. and it contains maps and tables by location, and it's a pretty useful gross estimate tool, even though it's considerably dated. 1995, 2020, it's almost 30 years old. If anything, however, as a nation, we have improved our water conservation practice, and so I would imagine most of the numbers in here would be upper support numbers, higher than is likely to be used today, at least in municipal use. So here's a particular example from it. There's many tables. This is table 4, and it has total water withdrawals by use category and state in 1995. And so you look at the different states, and everything's in million gallons per day. So Alabama, on average, for domestic supply, draws 62 million gallons per day. You could then determine the number of people in Alabama, and then that gives you a million gallons per day per people. And that would be at least a starting point to make a useful demand estimate for a particular application. Figure out how many people are served by a particular node. You now know what that node demand is, at least on an average level. The applying estimate is we can take different pipe diameters, and the plumbers work on how much water you can actually get. Now, naturally, these all depend on a particular pressure, and generally in plumbing, they assume the pipe velocity and supply is about 8 feet a second, which is the standard velocity used to engineer a plumbing system. So the plumbing diameter will limit the flow rate you can get. So the larger the pipe, the more water you can get. A home with 1-inch plumbing can use substantially more water than a home with 3/4-inch plumbing. Most supplies, or many supplies, at least in Lubbock, I think in my house, I have a 2-inch line coming out of the meter into the house. So I could conceivably use up to 80 gallons a minute if I wanted to. In my house, I have 3/4-inch copper. I know that because I've ripped tons of it out of the walls to make it quit leaking. And that can carry at typical residential pressures about 13 gallons a minute. So my house in Lubbock, I can use 80 gallons a minute. You could use that as a way to get another upper estimate of the amount of water you'd have to supply to a node. You assume that everyone's using the max amount they can use for a short period of time. That helps give you a maximum flow rate. Another way would be to consider the fixtures in a house that might be operated at the same time. Here's a diagram that shows different flow rates for different kinds of fixtures. If you add up all the flow rates for the devices you selected, you've just figured out the peak flow rate that house would need. So you would, depending on how many teenaged boys and girls you have in your home, you could just turn everything on and add all those numbers, and that's the maximum flow rate that your house would need. And then you want to think about continual water use, anything that runs for more than 10 minutes. And that gives what an estimate of something called a service flow rate. So you could do that per house, especially if you're doing a new subdivision design and it's going to be built out with perhaps not similar looking, but similarly configured homes. That would give you service flow rate and peak flow rate for each house multiplied by the number of houses. Bingo, you got an answer. Another tool is this rural estimate from the 90s. For private water systems, and this is more for sizing your well and your pressure tank in a relatively remote environment. But again, it gives a estimate of the minimum flow rates that would be expected. So a 6-bedroom home is at least 18 gallons per minute, and the URL for the reference is shown there. And then the TCEQ RG195 has a set of gallons per person per day for different other oddball institutions. Hospital and institutions other than hospitals, prisons, universities, not to be confused with country clubs, um, are probably the highest users in gallons per person per day. And then if you go to a prison where you're not allowed to use toilets, bathe, or eat, your water use is way down. So using the estimate, we would estimate the need per connection to size the system, and then we'd run a hydraulic model at these values, either to size the pipes or to answer the question, can I produce the pressure I need throughout my network? Then we want to estimate demand to determine how likely the system is to perform in terms of pressure zones and such. So we could run the hydraulic model at different values to check pressures without fire flow and repeat with fire flow to check that minimum pressures are maintained. So next time we're going to do an introduction to EPANet, how to install on PC and Mac, and then a set of examples. Let's go ahead and take a look at the exercise set for relative to a subdivision and see how we could estimate demand. So the first thing the exercise asks is list the different types of hydraulic elements, and this is, so you presume there's an EPA model here. And so you're going to have to look at all the pictures and look at the EPA manual to find out what each of the pictures means. Same thing if you're training for food service. You'd have to figure out which pictures correspond to which kind of hamburgers. Next thing is describe how to estimate demand for the water distribution system. Well, I would look at this and it says each lot will house an executive home. So I could go back to this picture, if I ever get to it. And probably from something like that, figure out worst case for an executive home in terms of peak flow and then service flow, and at least make my initial estimate from that. And then I start counting lots. 1, 2, 3, 4, 5, 6, 7, and come up with the total number of lots. Then I know the gallons per minute per house. I know the number of houses, so the product of those two would be the total demand estimate for the entire system. And then let's see, the remainder of the problem is stuff that you can do in your computer spreadsheet, although it's an EPANet problem. So that's pretty much what there is to demand estimation. We'll take a look at circular 2000 or 1200. And I just, hopefully I picked a, so in it, it has different maps of places, has per capita use, for instance. So this is also another good place to estimate the use. You notice Texas is a pretty big water user, and that's a consequence of the size of the state. Doesn't mean we're particularly wasteful. That gives you a good average estimate. If we also look at other reading material, water distribution systems, this one has a nice discussion on water use and demand, residential, commercial, and industrial demand, water consumption for some different types of land uses, peak demand versus average demand by state. You can, yeah, they have the wrong code. That's interesting. Pressure requirements, and then this is important. This is a peak ratio based on system size. So it's the ratio of the maximum hour to average annual use and maximum day to average annual use. It has some discussion on fire flow. An example set of calculations, how to pump water. And I believe this is the source of a curve that allows us to do time varying flow behavior. Assuming I can find the curve. Oh, let me scroll up here briefly. Here's an example of why we want to control velocity, because we can have substantial forces as we make water flow through a horizontal bend, just from the momentum transfer alone. Discuss the system layout, fire hydrant location, and very good discussion of a lot of what you'll need to know. Has the Moody chart, but we found an alternative for that. It has the roughness factors for Hayes and Williams application. Introduces the concept of equivalent pipe lengths, which if you're doing computations by hand is often easier than using the kV squared over 2G thing for fittings. You just make the simulated pipe long enough to account for the fitting losses and then solve directly. It discusses a manual method of doing flow calculations. That's the Hardy-Cross method. Has a drawing. Oh, it didn't have what I was looking for. Oh well. That comes in a later chapter, but there's also charts that allow us to take an average day and then incorporate the hourly variation within a day. And we will get to that when we get to that. Okay, that concludes this video on lesson 8, water demand estimation.